Hi, in this video we're going to create a boundary scan test using the JTAG Circuit Test software, and we're going to see how easy it is and how quickly you can create a new boundary scan test that's going to be easy to run and will provide circuit level and pin level diagnostics. So to get started, we'll first introduce this test board, which is a Xilinx eval board. It has 4 JTAG components on it, including a CPLD and an FPGA. It has some DDR memory. It has LEDs, switches, and it is connected via a test access port and ribbon cable to a port on a USB-based 30 megahertz JTAG controller. This controller is called the Flint Systems on-tap controller. It has 2 channels, so you can run multiple JTAG chains, and you can have multiple controllers in one application. For those not familiar with boundary scan technology, it's based on an IEEE standard, and it consists of a series of cells in the form of a boundary register in each device that supports JTAG. Basically what happens is you have test data in, which goes through some boundary cells. Each of the cells supports both application mode and test mode. In application mode, the signals go right through the cell. It becomes transparent, and they go back out too. So the application is not affected by, except for a small amount of timing, it's not affected by the boundary scan implementation. The cells are connected. They lie between a pin on a device and the internal logic. In test mode, data comes in to a cell and is propagated through the boundary register through all of the cells to a test data out port. That can be concatenated to the test data in on another cell or another chip, and then around the boundary register, and finally ultimately out to a test data out pin connected to the TAP, test access port, on your target board. So the cells are connected to each other in this serial boundary register fashion, and the implementation is described by what's called a boundary scan description language file, which comes from each vendor, and that shows how the test access port is configured, the ID code. It shows all of the pins and cell connections in a particular BSDL implementation. To get started, what we will do is click on the application button in the upper left of the user interface, and we're going to open a new project. The project folder needs to contain all of the BSDL files that you're going to need. We're going to base this project and build a project with just the BSDL files. You can include a netlist, but in this particular instance we're not going to do that. We're just going to go to the folder with those BSDL files, select it. The BSDL files will then be listed here, so you want to be sure you have those files. Again, we're not going to use the netlist. We're not going to use any bill of material information. We're just going to go ahead, select this folder. And now the BSDL files will be listed here. But in order to develop an application, we need to define a JTAG chain, which will be listed in this column. Now we could drag and drop these BSDL files over here and put them in the correct JTAG chain order. But to make things a little easier, we'll just click on this auto detect button, and that will show how the software has found the BSDL files in the corresponding devices in this test data in to test data out order. And what we'll do is just add these detects to the JTAG chain, and the software will assign a default reference designator. But what we can do, since we know the devices on the board, we know that this first position for this device is called U4. The next one is U3. The system ace is U2. And this FPGA is U1. And they're all in JTAG chain A. We could change that easily enough if we wanted to. Say we had multiple JTAG chains in the application. So we're now ready to accept this. We have the chain defined. So we'll click OK. And now the software is showing our chain here, U4 to U1. And we want to do a couple of things before we get going with the test. One is just make sure our controller is set up so that the ports on the controller match the JTAG chain. So the first port is port A, and it's connected to JTAG chain A, so that's good. And it's running at 9 megahertz. If we wanted, we could change that, but that's the default. The second port has no connection, so we're going to set that. It's not connected to any channel or any JTAG chain. And then we're going to come over here and save this adapter file. The other thing that we should do is in the circuits list, it's a good idea to let the software know what nets are power and ground nets so that we're not trying to drive any JTAG pins that might be connected to those nets. So what we'll do is we'll show the nets, and the nets by default are ordered by highest pin count, and so ground nets typically have high pin count, so we're going to assign these pins as ground. And then let's see, the power pins, we're going to assign some of these pins as power. We're not going to get them all for now, but that's the idea. You want to go through there. Here's a ground pin. We want to identify that as ground. So let's just take a quick look. VCC int. I think I want to do that as a power pin. So at this point, we're ready to go. So we can simply, well, before we do a test of everything, let's check the tap. We're going to test the tap. And the reason for that is, although when we did the auto detect, it used the tap and the tap pins and ID codes to identify the chain, but we can do some additional things because the JTAG implementation is really our test instrument in the device, and we want to make sure that it's good. I'm going to run this test one more time. And what it's showing us is that a bypass register was tested. It's good. It's showing us the ID codes, and it's checking the length of the boundary register. It expected 2,295 cells in the 4 devices connected together, and it measured 2,295, so that's good. So at this point, we could go in and do a number of things, but let's go back to the circuit, put our circuit up. and we will run all pins. And what happened here is the software broadcast a signal on every I/O pin, and then it looked to see which pins received that signal. So in this instance, for example, pin R1 is shown connected to P1. So these are the detected pins. Clicking on pin R1 brings us to the corresponding R1 in this list of pins on device U1. And we could check this out. We can see if this pin, if we were to place a signal on it, if we were to drive it high, does it go high? If we were to drive it low, does it go low? So this P1 does follow R1. This down arrow means low. So, and then if we wanted to, if we were confident that's a legitimate connection. Now bear in mind, we don't have the net list, so it could be going through resistors, resistor pack, whatever. So we could we could just say connect to this pin and resolve that question right here. But the other way we can do this a little easier is just learn the results that we got. So we just learned them, and we'll rerun the test. And it passes. So we now have a test. So at this point, let's just, for the heck of it, close things up. I like to do this and start and make sure we can save and restore. So if we go to our list of solutions now, that will show us in this project folder, the last test run was this one, CTBSDLs, which is the name of the test that we just ran. You can also do it through a list of most recent. So we're going to load it up, rerun the test. So we have our test. Now let's see if it actually detects faults. So what we'll do is introduce a fault by switching one of the dip switches and then rerunning the test. And now it's showing a fault, the red dot, and it's showing that pin T7 is failing, and pin T7 is in fact connected to the switch that I flipped. So the diagnostics are working. So with just that amount of effort, we have created a good structural test. We didn't have the net list, but at least all of the things that can be connected and the paths through the circuit that can be detected from one scan pin broadcasting to other scan pins receiving has been checked out, and the diagnostic message is pretty clear. So we're ready to go. If we fix the fault by flipping the switch and rerunning the test, it now passes. So just a few other things to let you know. You can, in the circuits list, you can wiggle particular pins. Like, let's say you pick a pin and you just want to wiggle it, not everything. It's going to show, okay, this pin is connected to U3 pin 8 is connected to pins 24 and 20 on U3. And if we had the net list, we could show that over here that U3 pin 8 is connected to a resistor in a resistor pack. And we could work through that, go browsing back and forth, and it would indeed take us to these other pins. So that can be done. Another thing that you can, and at any time you can wiggle pins if you just want to wiggle a pin and see what happens. You can always wiggle the pins. if the board is off, you can even bring test results back by just doing that. That will recover your last test results. Another thing that you can do is monitor all of the signals, active signals on the board, or you could pick one signal that you'd like to watch in application mode and watch it, turning the software into a very slow logic analyzer. So we could just say show place in connector list. So U3 pin 8 is now in the list. It's not switching, so it's just showing as a level low. We'll stop that. Let's see what else. Let's go back, rerun the tap test. It's still passed. Just to show you what happens if I turn the test board off, the failure will look like this. So you'll know you had a failure. I've turned the board back on, and it is running. Your tests will be shown at any one time. You can look, the solutions list will show you all of the tests that you have. If you want, the tests are created in what's called a test suite creator. You can select pins and put them in what's called a test suite runner, and then once you have some tests in that runner, I just put that in the runner. Let's say we want to run the test. That test, we can run it with this switch. So once you've created a suite of tests, you might have script tests, you might have interconnect tests. You can put them here, and one flip will, one hit on this button will run the whole suite, and you'll get the pass or fail message next to it. And the diagnostic results will, if you bring any one up, you'll be able to look at the diagnostic results. The other thing is there's a file viewer, so if you want to look at, say, a file or something like that, you can look at it in the viewer. So we'll call it quits for now on this video. The next video will show how to do the same thing with a net list and how much more you can do with a net list. And then we'll also show how to write script files, and we'll look at a few of the other features in the software.